Hey guys. So today we're going to go over early atomic models and discovering atomic structure. Uh, this is sort of all leading up to essentially the background leading up to how atoms were discovered and all the information about them. Okay. Some of this you probably already know. You can read through this. I'm just going to hit the highlights and explain some of the things. So we have early atomic models. Aristotle, an ancient Greek philosopher, had originally thought that all matter was made of a combination of four basic elemental forces: earth, air, water, and fire. Um, then along comes this guy named Democritus, who thought that all matter is made of small indivisible particles called atoms. The problem is in 450 BC, you couldn't see them, and they had no way of determining that they existed at all. So this idea was essentially thrown away for over 200 or 2,200 years. So imagine that you have an idea, and over 2,200 years later, people start coming back to that idea. So that'd be like in the year like 4,200, whatever. Like that's pretty crazy to think that somebody had that idea that far ahead of time. Right. So how does this work? Okay, how does it work where they try to figure this out, something that you can't see? Well, a guy named Antoine Lavoisier discovered the law of conservation of matter. Right, the law of conservation of matter essentially says that matter cannot be created or destroyed. It has to come from somewhere and it has to go somewhere. Not in the same form; it can be changed, but it has to be there. Right? So, Antoine Lavoisier used bell jars to burn items and contain all the matter, solids and gases. He then compared the beginning and ending masses and found them to be equal, showing that even though visually the amount of mass went down, there was still actually the same amount of mass there. A bell jar, if you're wondering what a bell jar looks like, let's see. These are what bell jars look like. Okay, it's just a glass covering, and essentially what he would do is he would uh, um, put something inside of a bell jar. He would take the mass, burn it, and then we know there's ashes. It doesn't look like there's as much there, but the gases that are produced that you couldn't see were kept inside the enclosed area. Okay. And this proved that even though it's in a different form, all the matter that was there originally is there at the end. All right. Then along comes somebody named Joseph Louis Proust, and he came up with the law of definite proportions, which states that a given compound contains the same elements in the same proportions or ratios by mass. All right. What does this mean? Well, if you have an element that is, I'm going to put this down here. All right. If you have an element, say water, okay, and I'm just kind of doing these numbers off the top of my head, but let's say water is, I think it's 11% hydrogen and 89% oxygen. This is of the masses. All right. What the law of constant composition or the law of definite proportion says is that all water is going to be this percent. So if you have, let's say, if you have 100 gallons, then 11 gallons will be hydrogen and 89 gallons will be oxygen. Now, I know gallons is a volume. This is just generically the idea. This should actually be by mass. So I guess if I want to be really accurate here, I'm going to change this to, let's say, grams. Okay, if you have 100 grams of water, 11 grams would be hydrogen and 89 grams would be oxygen. Okay, no matter how much you have. So if you had, I don't know, 1 million, if you had 1,000,000 grams, okay, you would have, let's see, 110,000 grams would be hydrogen and 890,000 grams of that would be oxygen. It's always the same ratio. That's the key. Always the same ratio by mass for a compound. Okay, it has to be locked in that ratio or else it's not the same thing. Okay. So, after these guys, in 1803, a guy named John Dalton comes along. And he was, I think he was like an English school teacher, and basically like every other good school teacher, he took other people's ideas, stole them, and put them together and tried to make them make sense. So he came up and put together this atomic theory of matter, the idea of what is matter. So he had 4 aspects to it. Every element is composed of small particles called atoms. All atoms of an element are identical, but different from those of any other element. So this means that he had the idea that all gold atoms are the same, but gold atoms are different from silver atoms. Okay. We now know that some of this isn't true. Okay. We know about isotopes and stuff like that already. We did this a little out of order. Normally I do this first, but because of how our days fell, I'm doing this now. Third one, in any process, atoms are neither created or destroyed. That comes from the law of constant composition. And a given compound always has the same relative numbers and kinds of atoms. Right? That means in a compound, like if we go back to our water example, okay, water always must be H2O, 2 hydrogen to 1 oxygen. Okay, now that might seem silly because we all know water, but if we change this ratio, even if we had the same elements, so if we changed it to, say, H2O2, that actually makes it a totally different substance, even though the same elements are there, because it's a different ratio. This is actually hydrogen peroxide, which is the stuff you can buy like at Walgreens or Walmart that you use on cuts that comes in the brown bottle to disinfect. 2 totally different things. And the reason they're different is because they come in a different fixed ratio as a compound. Okay. So Dalton said, a compound always has the same relative numbers and kinds of atoms. It's in the same ratio. If it's not in that ratio, then it's a different compound. All right. So I'm going to stop there with the early atomic models, and we will hit discovering atomic structure in a second.